My presentation title is Lyapunov function and stability of solutions of stochastic differential equations with fractional-like derivatives. You know, over the past decades, we have very rapidly development of fractional analysis. Now we have various variants of functional derivatives because this kind of derivatives have been widely used in the study of memory properties and other properties like hereditary properties for very complex systems in different areas. I have a list of sources. I try to show it. This is a literature. This is a publication last decades from scientists from very different countries. I would like to attract your attention to publication number 3 and 4. Publications number 3 and 4. This publication belonged to Abdul Jawad and to Khalili et al. And this mathematicians first include to mathematical literature new notions like comfortable fractional derivatives and Journal of Computer and Application Mathematics in 2015. Abdul Jawad have a publication under this title, and this is new fractional derivatives. You know, we have many different fractional derivatives like Riemann-Liouville derivatives, like Caputo derivatives, Liouville derivatives, Weil derivatives, etc. But comfortable fractional derivatives, which belong to Abdul Jawad, it is another thing. This is more closely to ordinary derivatives than others. Okay. Also one bibliographical things. I would like to talk about publication of academician of National Academy of Ukraine, Professor Martinyuk Andrei. Martinyuk and his students, his followers, do very too many about system of differential equation with derivatives, with fractional-like derivatives. In this publication, I also need to reminder this very famous name, like Professor Lakshmikantam. Lakshmikantam and his schools, together with Martinyuk and schools, developed very deep analysis. I mean, stability analysis of systems of fractional derivatives, and I try use little bit this result in my research. Also, unfortunately, I need to introduce my student, my follower here near me, Mr. Rakhmatov Jamshed. He worked with me about 6 years, And I also have one other my students. This is Kholik Nazar Kuchakshoyev. Now working in Khorog. It's very far from Dushanbe. And this my students. I very for me it is very good, very comfort, because I have students like Jamshed and Kholik Nazar, and this my our publication, my presentation also it is consist results which we have jointly with my students, with Jamshed and with Kholik Nazar. And this my presentation devoted to the stochastic equation, because in deterministic systems we have many results, not with fractional-like derivatives, but derivatives, fractional derivatives in other likes, okay, in other variants. And the mathematical theory of stability of solutions of stochastic differential equations consists of two main research directions. First, this is a very old but very strong direction. We know we say Lyapunov method, or direct or second Lyapunov method for stability, for analysis of stability of system. And also we have Barton's fixed point method. Barton is an American mathematician. He also he is live. He work very intensively, and Barton and his school, mathematical school, have another point of view about stability, mathematical theory of stability. The question of existence, uniqueness, and stability of solutions of stochastic partial differential equation were the subject of analysis, and this is a list of publication. I mean 16 Saktivel, Rivalti, Pen, Yuri Gliklich from Voronezh. Also, people like Trigesson and et al. The Lyapunov approach. It is okay? You hear me?
Yeah, sure.
Okay, thank you very much. And also mathematicians like Alexander Veretennikov from Moscow and others, people which deal with stochastic equations. Okay. My presentation concretely devoted to the development of Lyapunov type functions for stochastic equation with fractional-like derivatives of the form 1, 2. Here, the D, this, I don't know letter, it's Gothic letter, D, alpha T0 is a fractional-like derivative. I have above I have a definition for this kind of fractional derivatives. Okay, B, this is a term for reaction-like, for SNOS, I don't know. And sigma, this is a diffusion term. This diffusion term, we have in this diffusion term, we have both B and sigma is a measurable function, and WT, a scalar Brouwer motion defined in the complete probability space omega phi and f phi t. This is algebra of This is a счетная algebra. This is a Cantley algebra. P is a как это вероятность наша, да? Probability, okay? And also we request to this to the stochastic process that W0 is equal to 0. E, this is an exception or mathematical no waiting, but okay. E, this is a statistical characteristic of stochastic process WT, and also we have other statistical characteristic. This characteristic name is a correlation function. Correlation function is equal to T minus S, and we know in stochastic analysis we say dWt by T. This is Wiener, a process of Wiener process. Okay, WT, there's a Brownian motion, but dWt dt, this is a also stochastic process. This is the Wiener process. Okay, for each T is from half of line, we denote space like LT, algotic T. It is L 2 omega phi and P. Okay, this is space of all sigma T measurable, Ft measurable space square integral functions who from omega to or such that norm of U is a mathematical expectation from U and degree 2. Okay, I want to stress that notion like random value, this is element of this space which we define like вероятностная тройка, like triple of the triple probability triple. Okay. In the case of Caputo fractional derivative, the existence and uniqueness theorem for equation 1 was established by the method of contraction mappings. Okay, if we have if we request from sigma that this function is a Lipschitz function, then we have a existent uniqueness theorem for equation 1. In this case, function b and sigma are required to satisfy the Lipschitz condition. Our presentation is structured as follows. Section 2 presents the definition of fractional-like derivative and studies the properties of this derivative. Section 3 is devoted to the concept of fractional-like derivative of Lyapunov type functions. It is shown that for some simple Lyapunov functions, the fractional-like derivative is majorant for the Caputo fractional derivative of these functions. Section 4 contains a fractional-like version of Ito's formula. This is a little bit new because Ito formula very difficult features, very difficult mathematically formula, and each each time, every time when we try to write Ito formula. Ito formula is this is like differentiation. We have a Ito integral, and also we have Ito formula. Ito integral, this is integral, and integral which which need for stochastic processes, because we cannot use integral like Riemann or Lebesgue for stochastic processes, because this kind of integral we can use for function, a little bit better function. This function may be continuous, maybe it is not continuous, but point in which we lost the continuous. This is county, okay? Or Lebesgue, a little bit more general situation, but this is also Lebesgue integral close a little bit to Riemann integral. But Ito integral totally another conception. It is not conception like Lebesgue or Ito and many other integrals which we have for deterministic case. In stochastic case, we have Ito formula for integration, but Ito formula, this is a differentiation, stochastic processes, it's another formula. And in section 5, this kind of sufficiency, we have sufficient conditions for stochastic stability, or stability and probability. That is two names for one concepts. Okay. Also, we talk about asymptotic stochastic stability and exponential stability in this section. Finally, in section 6, we provide concluding remarks. Okay. Fractional-like derivatives, I give definition 2.1. Let alpha between 0, zero not include to this interval, but 1 include to this interval. Alpha can be 1, but cannot be 0. And then we have R plus, it is alpha of set of numbers. T0 belong to R plus, and ft function from T0 infinity to R to O is a given continuous function. Definition 2.1, for any alpha from 0, 1, so from this alpha of interval, fractional-like derivative d alpha T0 ft of order alpha of the function phi is defined by the equality. You can observe that if we give alpha equal to 1, then we have ordinary derivatives. Okay. If alpha is equal to 1, then we have a d1 T0 ft, it is a f prime tab. Okay. If t is equal to 0, then this our derivatives will take another form. For the case t is equal to 0, we use another relation like here. If the alpha exists in 0b, in interval 0b, then because we firstly we have a definition for derivatives and point. Then we can talk that this derivatives like ordinary different derivatives exist in interval no b. Then we have this equality. It is if it's a fractional like derivative of function f ft of order alpha exists and is finite and t0 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 infinity, then we can say that ft is we say that ft is differentiable on t0 infinity. Small remark like remark 2.2, definition 2.1 does not satisfy all the conditions that they are true for Riemann-Liouville, Caputo, and other derivatives. For example, in this limb we collect properties of this kind of derivatives. We have, for example, we have properties 2. D alpha t0 from function t p degree p is equal to p by t minus t0 degree 1 minus alpha t p minus 1. If we give p is equal to 0, because p is from or any number, okay? But if we take p is equal to 0, then we have d alpha t naught from 1 is equal to 0. Is equal to 0 because p is p equal to 0. But this property is not true for Riemann-Liouville derivatives. This kind of derivatives may be this property is like a little bit simple, but it's very important properties for this kind of derivatives. About proofs, we have no problem because this is a differentiation. Differentiation is a linear operation. Linear operation have this properties like 1, for example. And also we have for multiplication this kind of derivatives for f to g for
product rule.
For what? Product. For production and also for деление. Как говорим деление?
Divided.
Divided, for division.
Product rule here.
And also we have like this properties. If fractional-like derivatives from ft is 0, then ft is equal to c. This property is very simple, like ordinary derivatives. The equalities 1 till 5 from lemma 2.3, similar to the classical results of mathematical analysis for integer orders of derivatives. This statements do not hold for the Riemann-Liouville and other fractional derivatives. I would like to stress that fractional-like derivatives, but this
Мамадшо, звук потерялся.
Потерялся?
Да, okay.
Lemma to 5.
Okay, now, okay.
Okay. Lemma to 5, if we got alpha between 0 and 1, and function h is a composition of m and g, is differentiable with respect to g at f for all t from or plus and function J at t is alpha derivative table for t minus for t non equal to t0 in gt not non-zero. Then we have a formula like this: d alpha t null m prime gt and fractional-like derivatives from function g. Fractional-like integral of order alpha is introduced by this formula E alpha t null, like this. It is a same for example Caputo derivative, but not equal. It is little bit another, little bit another. Not we cannot say that this integral and integral fractional integral for Caputo, it is same. Little bit another formula. Also, we talk about next result. It is lemma 2.6. If we have ft in all infinity to r or is alpha differentiable, then for all t greater than t0, the following ratio is true. We have a operation of integration. We have an operation of differentiation. This composition is not equal to 1. This composition is equal to ft minus ft null, ft0. Okay. This is information about fractional-like derivatives. Now, I talk about Lyapunov function and its fractional-like derivatives. You know that Lyapunov method is a very old method. Lyapunov method started in doctoral dissertation of Alexei Mikhailovich Lyapunov, great Russian mathematician. About 1898, he published a book in Kharkov in 1889, and more than I don't know 125 years.
Я немножко голос опять уж пошел.
Нет, у меня какой-то шум есть.
Yeah.
Там нет у вас?
Не, все нормально.
Хорошо, спасибо большое. As a research tool, the second direct method uses some special functions called Lyapunov function. The real continuously differential function v from t. This is the interval and real line. T. This is not plus. This is a multiply to. This is a direct multiplication. T by b or is a ball, and Rn I means Euclid space vector Euclid space. V from this direct multiplication to or, which satisfies condition v t0 is equal to 0, is said Lyapunov function. Here B or denotes the ball of radius or centered at the origin of the space with this norm, and T denotes the interval of real number line, where A is minus infinity or some infinite number. We call the derivative V with this point of the function Vtx by virtue of the equations. Equations like this. Xt0 is t0, bt0 is 0, because we need for null for solution or no solution. We have for this derivative v point this function dv dt, and this sum. We can write to перевод. Не может, да? Сюда не может двигать. We have this kind of formula for derivatives of v for Lyapunov function. Fx equal to xt is the solution of this equation. Ordinary system differential equation 3.1. Then v point represent the total derivative of complex function Vtxt with respect to time. It should be noted that calculating v point, there is no need to find the actual solution of systems 3.1 xt. Further, by k we denote class of function. The omega e u is equal greater than equal to 0. E not natural number. This is scalar continuous non-decreasing functions such that omega e0 is equal to 0 and omega eu more greater than 0 for u greater 0. The existence of classical Lyapunov method lies in the validity of the following classical three theorems. Two theorems, theorem 3.1, 3.2. This is Lyapunov theorems. First, for first time, Lyapunov have a formal relation, have these theorems. That there exists a function Vt or x such that we have this then the solution, and also other theorem for more exact inequalities. F omega 1 less than equal to v and v less than equal to omega 2. Also, derivative of v less than equal to minus omega 2. Then the trivial solution asymptotically stable. You know that asymptotically stable is a stable solution, and also the solution tends to 0, it tends to the infinity. Also, we have very classical, very famous Steif theorem about unstability. If in domain, this domain, the inequality v point more than omega 4, another function, but all this 4 function belong to k, okay? Then the trivial solution is unstable. This is I remind classical theorems. Now, unfortunately, in stochastic cases, we cannot use directly these classical theorems because notion of derivatives for Lyapunov function is not there. In this direction, the purpose of our presentation is to extend their both statements to the case of problem 1, 1, 1, 2 to I means to problem Cauchy problem for stochastic differential equation, and this regard note the instead to the usual derivative in theorems 3, 1, 3, 2, and 3, 3, we have to use the Dini derivative. Dini, following Dini derivatives for the Lyapunov function. This kind of derivatives we call Dini derivatives, okay? 3.4. And 6, I can show to you 6. The concept of fractional-like derivative introduced the same way for equation of the form like this, because here we have a fractional derivatives. Please, 6, I think, is Martinyuk. Definition 3.4. Let V be continuous and alpha differentiable function. I means differentiable order is alpha. V like this. T0, x0 is the solution of problem 3.5, 3.6. Then for this pair, Tx from or plus in B or, this is a ball in the Rn. The expression, this expression like this, 3.7, is the upper right fractional-like derivative of the Lyapunov function. You know, when we talk about Dini derivatives, we have 4 derivatives, like upper right, upper left, lower left, lower-like derivatives. This kind of derivatives of the Lyapunov function determine it accordingly to 3.7. Okay. Now we talk about what? Lemma 3.5. Let V be continuous, alpha differentiable in locally Lipschitsable function with respect to second variable x on R plus multiplied by P or. Then the fractional-like derivative of the function Vtx with respect to solution is defined like this. Lim sup, where Tx is belong to R plus multiplied by B or. If we don't depend on T like this, if function V differentiable with respect to X and function X alpha differentiable with respect to T, then we have a formula like this. Examples of Lyapunov function V1 is a x and square x from or. V2 is this is a 2 vector. One is a column, other is span. For x from Rn. Also V3 this is matrix. This is matrix function. If x belong to Rn are given and their fractional-like derivatives are calculated, where P is n by n matrix. The following statement was established. I think I talk about Maserant. I said in the beginning of my presentation that fractional-like derivatives is Majorant for Caputo derivatives. This 3 inequality and lemma 3.6 show this statement. This means it follows from lemma 3.6 that the fractional-like derivative of Lyapunov function is an upper bound majorand for the fractional capital derivative of the same Lyapunov functions. This statement, this lemma we need for provement stability, probability stability, asymptotical probability stability for stochastic equation, and we have like this statement that set of function with capital derivative is smaller than set of function with fractional-like derivative. So I means that the function with fractional-like derivative is much more bigger than others. Okay. Now at this point, this chapter, I talk about Ito formula for functions with fractional-like derivative. First, we give the definition of the solution to the problem 1, 2. I talk about, I was talk about Ito integral, Ito formula, and unfortunately, every time when we want to do analysis of resolvability or analysis of existence and uniqueness of class of differential equation, we need to have integral equation is equivalent to differential equation, because we can work with integral equation and much more easy work with integral equation than with differential equation. Every time we try to find equivalent integral equation. For one, it is a integral equation for stochastic differential equation 1, 1. It is not so difficult for understanding, because in kernel of integrals we have s minus t0 and alpha minus 1 degree. This we have kernel like this because we have a fractional derivative and left part of equation 1, 1, and then we can write this integral equality. We make the following assumptions. A1, there is a constant L, positive constant L, such that for all x tilde from or, I mean, this is scalar function in this case, because we work with Wiener processes. We in our equation 1, 1, Wiener process is not vectorial. This is a scalar function, and depend it we have a assumption like A1. This is this kind of assumption. It is very close to Lipschitz condition, but it's not totally Lipschitz conditions. And it is another A2. This function sigma is essentially bounded like this, and also sigma is L2 integrable. We have an integral like this. Then we can try to prove lemma for 2. Suppose that A1 and A2 is satisfied. Then for alpha from 0, 1, problem 1, 2 as the unique solution X, which belong to Sequay integrable function, but the definition set of the definition is this triple, the probability triple. Omega is universal set. Sigma t it is a algebra of sets. In this case, this is a algebra of subset, all subset of set omega, and P is probability. This is a measure, okay? This kind of solution given in form 4.1. This is integral 4. Next, we present a new version of Ito formula for function with fractional-like derivatives. This formula defines the rule for differentiation functions of stochastic processes with fractional-like derivatives. Let Wt be standard scalar. This is also scalar. Rho in motion, C introduction, and let V function like C1, 2 denote the family of all valid function omega defined in continuously differentiable with respect to Z. Next, please. Let also Z is the Ito process for this stochastical equation. This is linear stochastic equation where B from L1 and sigma from L2. Let us recall the standard one-dimensional Ito formula. This is Ito formula. Okay, we can have a differential for stochastic process y. Dyt is equal to this presentation, to this formula. We can write dy through y partial derivative z partial derivative degree 2, and also this function y z from tzt and this stochastic term. Let now t is bigger than 0. Suppose that x tilde is an Ito process for this equation for 2 with initial conditions, lemma 4.2 and formula 4.2, 4.3 here imply that there exist unique solution for T0 from 0T of the form like this. Note that when T belongs to 0T, 4.2 is equivalent to this operation, 4.4, where we have a function like from L1 and from L2. This is coefficient for B. This is we can say that is a viscal bonus weight for B and weight for sigma. And we have we will deal with integrable function degree 2 with weight. Okay, we're now ready to present a fractional-like version of Ito form. This is a formula for fractional-like versions. Let y like this, then y is the Ito process given in the forms of the following formula. This is Ito formula. I have a proof of this formula. Proofs came from lemma 4.3 by virtue of 4.4. We will obtain this relation. This is our formula. Next, please. Now we go to main result of our presentation. This is a stability, stochastic stability. First of all, I would like to see to talk about stability in general. It is well known that the question of stability of some solution of equation 1 by means of change of variables can be reduced to an investigation of the question of the stability of trivial solution. For this, we need a condition like this. BT0 is 0, sigma T0 also is 0. And then we have our equation under this condition, our equation has a trivial solution, if we talk about stability of trivial solution. Stability of trivial solution of equation 1.1 is understood as the property changes little with a small change in the initial condition. Depending on the specific understanding of the expression, small change in solution, different definitions of stability are possible. Okay, we have a like first definition about trivial solution of equation 1.1 is called stochastic stable or stable in probability. For each pair, epsilon and L exists number delta, such that this probability is more than 1 minus epsilon. This is a stochastical stable. Otherwise, such solution is called stochastical unstable. If we cannot find for epsilon the data like this, then we have a stochastically unstable. Also, another definition is asymptotical stochastical stable. Asymptotical stochastical stable, almost surely. It is another. It is a stochastical definition. Next, please. Unfortunately, I have not too much time. Lyapunov stability and asymptotic stability. We talk about it here. We have theorems that let the following condition satisfied. V1. There is a positive definite function V such that for all txt, this function with L alpha, like this is a formula of L alpha. There is a we talk about the existence of a full function like this. It follows from the definition of Lyapunov function, because we have a Vt0 is equal to 0. Moreover, there is a continuous non-decreasing function mu from k. We have a set of functions such that this inequality. Okay. This is statement for asymptotical stability. Suppose the condition A2, A1, A2, and V are satisfied for and also more than 0, less than 1. Then the trivial solution of equation 1.1 is stochastically stable. I do not talk about proof because I have time, small time. Another kind of stability, sur not, it is a, I think this is a asymptotic. Then. Then the trivial solution is stochastically stable. This is stable. It is theorem 5.4. And next, please. It is a proof. Okay. And also we have a condition for asymptotical stochastical stable. Okay. Next. Also, we can talk about exponential stability almost solely. This kind of condition we need, V3, okay? And then we have theorem 5.6. We have a very long improvement. It's like this, okay, okay. This is I think this is my main result of our presentation. Yes. Okay, very small conclusion. For deterministic, stochastic, and stochastic systems of differential equation with fractional derivatives of Riemann-Liouville, Kaputov, Grunwald, Letnikov definitions of Lyapunov function with fractional orders of derivatives are given in Martinyuk and Barton. However, the practical calculation of these derivatives is associated with great difficulties due to the absence of chain rule for them. For this kind of fractional derivatives, we have no chain rule. In this paper, the direct Lyapunov method is carried over the scalar stochastic differential equation with fractional-like derivatives, for which the chain rule for differentiation complex function is satisfied. For this purpose, a new fractional-like versions of the Ito formula is introduced. It is important the fractional-like derivatives, majorants for the Kaputov derivatives. Thank you for your attention.